Let's do some problems or examples on tensor products. Okay, so first problem. So we defined the tensor product of two Z modules. So now suppose I do the following. I take M to be any arbitrary Z module, but for N I will choose it to be the 0 module. Okay, meaning it's just the singleton comprising 0. So this of course is Z module, the trivial group if you wish. Then the claim is that if I take the tensor product of M with N, then this is also just the trivial group. Okay, so I claim that this is also just isomorphic to the trivial group. Okay, so let's prove this. So we just need to show that this tensor product has only one element. Okay, so what is the typical element of the tensor product? So recall, this is one of the facts. Every element has the following expression. Okay, any element of M tensor N can be written like this. As a sum Mi tensor Ni, okay, or some finite sum, let's say. Now Mi comes from M, but Ni comes from N, which means the only possibility is that Ni can be 0. Right? So what does this look like? It just looks like summation Mi tensor the element 0. Okay, but recall that this symbol, this tensor product symbol between M and N, this was our alpha of M comma N that we looked at last time, and that was a bilinear symbol, meaning this is the same as summation Mi tensor 0. Okay, now so let me just call this some M tensor 0. M is just summation Mi. Okay, so I'll just give this a new name. Summation Mi is M. Now this element M tensor 0 I claim is actually the element 0. Okay, so let's prove this. So claim is that M tensor 0 is the additive identity of this group M tensor N. Why is that? Well, let's again use the bilinearity. So 0 plus 0 is 0. Okay, so M tensor 0 is M tensor 0 plus 0. But now bilinearity tells me that I can split this into two pieces. Okay, so M tensor 0 is the same as two copies of M tensor 0, which means M tensor 0 had better equal the element 0. Okay, so that means what we have shown is that any element of the form M tensor 0 is just 0. Therefore, this module that we constructed, the Z module, it doesn't have any elements other than the 0 element. Okay, because we started with an arbitrary element and we showed that that element is just the 0 element. Okay, good. So that's the first problem. Now more generally, okay, let's take a second situation. Suppose M is a Z module. Then consider N to be Z itself. Okay. So I mean take the second module to be Z itself. So Z itself is a Z module. And what I'm going to do is just going to look at their tensor product. So suppose I take Z tensor M. Okay. So then I claim that what do I get? So we already did this. If you tensor with 0, then you get just the 0 module. If you tensor with the module Z, then what do you get? Well, you just get back a copy of the original module. The claim is that this tensor product is actually isomorphic to M itself. Okay, so let's prove this claim. And to prove this claim, what we'll do is we will use the universal property of the tensor product. So observe what does this proving this claim entail? You have to show that there exists an isomorphism from Z tensor M to M. Right? This is what we want to construct, an isomorphism between these two guys, and this sort of map from a tensor product to another module is given by the universal property. Right? So recall that if somehow you could construct, so this is the universal property of the tensor product. If you have a bilinear map to some P, then that gives you a unique map from the tensor product to P. Okay, so if you are trying to construct a map from the tensor product to any module, then what you should try and do is to somehow use the universal property of the tensor product. Let's do that in this case to see how it works. So let me first start with a bilinear map from Z cross M, and the target module here is M itself, right? So first let me try and construct a bilinear map. Okay, what should I take? Well, there's more or less only one thing you can do. Take an integer A, take an element x of M, just map it to A times x. Okay, I mean M is a Z module, so I know what scalar multiplication by an integer means. Now observe that F is bilinear. Okay, F is in fact a Z bilinear map. Easy to check because that's just the module property. If I take a sum of two scalars, I get this, or if I keep the scalar fixed and take a sum of two module elements. Good, so I have a Z bilinear map. Therefore, by the universal property of the tensor product, I have a map from here to here. Okay, and what does this map do? So it makes this diagram commute. There exists a unique map, we know that. And what is this element A comma x, right? What does that map to in this? So recall that was exactly what we called. So alpha of A comma x is what we had denoted by this symbol small a tensor x. Okay, so this map does the following. It maps A tensor x to Ax. Therefore, we have concluded there exists a unique, in fact, there exists a unique Z linear map such that which takes A tensor x to Ax. So this is just another way of saying it makes the diagram commute. Okay. Okay, good. Now claim is this map is an isomorphism. That's going to be our claim. Okay, claim is an isomorphism of Z modules, meaning it's an isomorphism of abelian groups. Okay, proof will show it's one-to-one and onto. So first observe its onto is clear. So we'll give this map a name F tilde. Okay, F tilde is onto because you just have to take A to be 1. Okay, so observe property 1. F tilde is definitely a surjection. So definitely every element x is in the image. So we just need to check that the kernel is 0. So let's try to understand what the kernel looks like. So let's take a typical element of the kernel. Okay, so let some element of the tensor product belong to the kernel, but this is again where we keep using this important fact that any element of the tensor product can always be written in this form. Okay, summation ai tensor xi. Okay, and recall this was just another way of saying that those EMN bars, okay, or the image of alpha that generates the tensor product. Okay, so let's pick a typical element. Suppose this belongs to the kernel. Any element can always be written like this. Okay, now this belongs to the kernel means what? I apply F tilde to this, I should get 0. Okay, but I know what I get when I apply F tilde, it's just the product ai xi. Okay, so suppose this is 0. Okay, good. Now observe the following, that the original element that I wrote down. So this is the conclusion, that summation ai xi is 0. Now this original element that I wrote down, so maybe I'll call this something, let xi belong to an element of the kernel. This xi can also be rewritten as follows. So this is summation but recall the bilinearity also says the following. So I will rewrite this as ai times 1, I will multiply it by 1, and this symbol here, this tensor product symbol, in other words alpha, the map alpha is bilinear, means that I can pull this ai out. So this is just nothing but summation. So we had this property, it's I can either write it as ai times 1 tensor xi or as summation 1 tensor ai xi. These are all properties coming from the bilinearity, right? Since this tensor product symbol is bilinear. Okay. When I put two elements there, it's linear in each component. Okay, good. Now let's look at this last expression. The element xi has this alternate expression here as summation 1 tensor ai xi. This means that xi equals, again I am going to use the bilinearity. So here we keep using the bilinearity in a very important way. Okay, so this is the same thing again by bilinearity. And now recall, this is just the element 1 tensor 0, because we have just shown that summation ai xi is 0. That was our assumption, that this element is in the kernel. So therefore this element xi we started out has this other nice expression, it's just 1 tensor 0. But now recall, that's exactly our earlier proof that 1 tensor 0 is actually the element 0 of this module. Okay, why is this 0, meaning it's the additive identity? Well, because the same argument 1 tensor 0 is of the form 1 tensor 0 plus 0, and you can write it as a sum of 1 tensor 0, 2 copies. Okay, so the same proof, xi is just the additive identity. So therefore what have we done? We started out with an element of the kernel and we showed that that element is just the 0 element. Therefore the kernel is 0. Implies f tilde is also 1 to 1. Okay, so it's a 1 to 1, I mean it's an injective map if you wish. So it's a 1 to 1 and onto map, therefore it is an isomorphism. Okay, which is what we needed to prove. Okay, good. So let's look at another problem, which is to show that to understand the tensor product of abelian groups. So suppose I take of cyclic groups, sorry. If I take two cyclic groups, z mod az and z mod bz, okay, imagine a and b are some numbers, at least 1. So I can always assume they are positive numbers. Then I claim that this is again a cyclic group Cz, where C is just the GCD of A and B. Okay, so let's prove this. So again our strategy is going to be the same. We will try and use the universal property to construct a map from the tensor product to this other module, and then we will show that that map is actually an isomorphism. Okay, so let's do this quickly. So from z mod az cross, so I need to start with the bilinear map. Start with a map f. What should we do? Well, let's take any two elements. So what's a typical element look like? M plus az coset n plus bz. And what can we do to this? Well, let's just map it to mn plus cz. So I'm defining a map like this. Okay, I need to always check when I define a map like this that it is well defined. Okay, so property 1, that this is a well defined map. Okay, why is it well defined? Well, if I change m or n to some, or both maybe, to some m prime and n prime, let's check well definedness. So if I change, so suppose I change the representative, to some numbers m prime and n prime, then the question is my final answer the same? Okay, is it true that m prime n prime plus cz gives me the same answer? That's what I need to check. Okay, let's check. What do I know? This tells me that m minus m prime is a multiple of a, right? Belongs to az. So a divides this. This property tells me that n minus n prime belongs to bz, meaning it's a multiple of b. Okay. Now let's look at what we have to prove, which is this guy. Let's take the difference mn minus m prime n prime. We need to show that's a multiple of c. Okay, but we can rewrite it as follows. Okay, just a little addition and subtraction of the same term. Okay, I've added and subtracted minus m n prime from both. Now observe, this is a multiple of b. This is a multiple of a. Okay, but observe that c is the GCD of a and b. So if something is a multiple of b, it's definitely a multiple of c. A multiple of a, for the same reason, is a multiple of c. So this both terms are multiples of c. So the net answer is again a multiple of c. Okay, which is what we needed to prove. Okay, that mn minus m prime n prime is in fact a multiple of c. So it's well defined. Okay, it's easy to see it's a group homomorphism. So to group homomorphism or a Z module homomorphism, if you wish. Maybe I'll just say it like that. Z. Oh, sorry. I should have said Z bilinear rather than. It's Z bilinear. So let's also prove that. So I need to prove it maybe. So let's show that it is Z bilinear. So in each component, it is linear. So the second property, Z bilinear. So if I look at m1 plus az, okay, what is f evaluated at? If I take a sum of two things in the first component, what is the answer? Well, by definition, this is just f of. So this is how you do addition of cosets, and this by definition is m1 plus m2 into n plus cz. Okay, but observe that's the same answer as m1n plus cz plus. Okay, so it splits into two pieces. So that's exactly f of m1n. Okay, so it's linear in the first variable. Similarly, you can check the other. Similarly, check n1 plus n2 is again a sum of two things. Okay, so it's in fact a Z bilinear map. So that's the second property. Okay, so I've defined a well-defined Z bilinear map from Z cross AZ, Z mod AZ cross Z mod BZ to Z mod CZ, and therefore by the universal property of the tensor product, I will get a map. Therefore, I obtain so I have this map F. So now okay, so there exists a unique map which is a homomorphism of Z modules. So there is a unique Z linear map F tilde such that the diagram commutes, meaning F tilde evaluated on what? Well, if I take a typical element here, so let me just call this m plus az as m bar and n plus bz as n bar, then that element here maps to m bar tensor n bar. Okay, so now my property here is that m bar tensor n bar is mapped to f of mn, okay, which was by definition mn plus cz. Okay, now claim is that this map is an isomorphism as before. Okay, claim f tilde as an isomorphism of z modules. Okay, let's prove this quickly. So what do we need to do? We need to check it's onto. Again, that follows from just taking m equals 1. So observe that f tilde of this was the definition. So just put m equals 1 and choose all possible values for n. So this is f tilde of 1 bar, sorry, m tensor n bar, right? So 1 tensor n bar is just going to give you n plus cz, and n now ranges over all possible values in z anyway. So therefore every coset is of this form in z mod cz, right? So this is onto for sure. Okay, choose n arbitrary, then you're done. Okay, it's again the injectivity that requires more proof, and the proof is almost along the same lines as what we gave for the previous problem, which is, let's take a typical element in the kernel. So let psi which is summation mi bar tensor ni bar belong to the kernel of this map. Okay, now what does this mean? Well, as before, let's just first rewrite it in this case. So this is summation. So what is mi bar? It's mi plus az, and ni bar is ni plus bz, but I can think of it as follows. I just take the particular coset 1 plus bz, okay, and I multiply it by the scalar ni, right? That's the z module structure on z mod bz. So I can just think of it as scalar multiplying the coset 1 plus bz by the integer ni, the scalar ni. Okay, and now again we use the bilinearity of this tensor product symbol, meaning the bilinearity of that map alpha, which defines the tensor product, which says that this scalar here can be pulled completely out of the tensor product, or equivalently you can push it into the other component. Okay, so I can move in some sense the ni from the second component to the first component. So let's do that. This is by bilinearity. Therefore this is the same as summation ni multiplying mi plus az. Okay, so this example is to give you some facility with manipulating expressions involving tensor products. It's 1. Okay, but what is this? This is just summation mi ni plus az 1 plus bz. Okay, and observe that the second component is the same for all terms, for all summoned. So I can again use bilinearity, make this into summation of these cosets mi ni plus az. So look at this coset of A tensor this coset. Okay, so what I've done is sort of rewritten my element xi, which was in the kernel, in this way, and now I will use the fact that xi is in the kernel. Okay, so xi belongs to the kernel means if I apply f tilde to this answer, I should get 0. Okay, so let's do that. So you take this, you apply f tilde. If you do that, you will get 0. Okay, applying f tilde gives 0. Okay, let's apply f tilde. So what is the definition of f tilde? If you go back and see, you are supposed to multiply these two elements, right? In this case, it's just summation mi ni into 1, okay, plus cz. That was the answer. Okay, so this is 0. That's what we have concluded. Okay, so xi belongs to the kernel, therefore means that this element here has to be a multiple of C, meaning it's in Cz. So conclusion that it's a multiple of C. Okay, but observe, but C, what is C? C was the GCD of A and B, which implies that if you recall what this means, you can write C as some linear combination like this for some elements P and Q in Z, right? The GCD of two numbers is always expressible as a combination of these. Okay, good. So what does this mean? So this summation mi ni, so what did I do here? So summation mi ni is of the form C into some number D, right? It's some multiple of C. Okay, so let's rewrite xi as follows. So xi was summation mi ni plus Az, okay, which I will write as CD plus Az, but C itself can be rewritten in terms of A's and B's, right? So I will use this expression now. So what will I do? I will write this as APD plus BQD plus Az. Okay. Now observe that this APD is already a multiple of A. Okay, so that already belongs to Az. So that term I don't need to worry about. So that's already in here. It's already in Az. So this is just BQD plus Az. Plus, okay, tensor 1 plus Bz. But now comes the interesting observation. So observe this first term has a B in front of it. Okay, so I will rewrite it as follows. I will think of it as B multiplying QD plus Az. Okay, so it's as if I am taking this coset and multiplying it by B, tensor 1 plus Bz. Okay, now again I will use the bilinearity. What does bilinearity tell me? It tells me that if I have this scalar integer in front, I can completely pull it out, or on the other hand, I can also push it to the second component. So here I'll just push it to the second component. This is therefore QD plus Az tensor B times this 1 plus Bz, right? So but what's that? That's B plus Bz. But observe B plus Bz is just 0 because B belongs to Bz, right? So this again is nothing but the 0 coset. And now we are back to the same thing. So I will call this QD bar again, this is 0 bar, and now we have already seen this. If you put a 0 in any one of the two components, then using the 0 plus 0 equals 0 argument, you can show that this is just the 0 element. Okay, so almost the same sort of idea as before, but just a little bit more complicated. Okay, therefore again the kernel of f is 0, therefore f is a isomorphism, f tilde is an isomorphism. So this is an interesting exercise because it says that, I mean, this tensor product thing is slightly non-intuitive. We started out with these two cyclic groups, Z mod Az and Z mod Bz, and what we constructed somehow is a sort of a smaller cyclic group, if you wish, right, whose size is equal to the GCD of the two sizes. Okay, so it's a sort of interesting gadget, and to some extent what you need is really a lot of practice manipulating these bilinearity relations, trying to understand how one can construct maps, what this moving scalars from one side to the other. Things like these are all part of the toolkit when you want to work with tensor products. Okay, so you should try and get a lot of practice doing these things.